So what we're going to do today is we're going to hopefully wrap up the last part of our discussion of the Java thread lifecycle. And this will give us a chance to talk about interrupts. And we've been talking about various ways of stopping Java threads. And last time we discussed how to stop a Java thread with a volatile flag, like a Boolean. But that has some deficiencies. And so we'll talk now about how to stop a thread with an interrupt request, which is a little bit more powerful. As part of this discussion, you'll also understand some of the differences between using a Java thread interrupt and a more traditional operating system or hardware interrupt, both of which have the same name, interrupt, but which behave quite differently. And so it's important to understand the differences. In addition, you'll also get a chance to see different patterns for interrupting Java threads. There's different ways to interrupt Java threads and handling Java threads, and it's kind of subtle. So we'll talk about some of the patterns for doing that right. So let's talk about how you stop Java threads with an interrupt request. So you probably recall that Java threads cannot be involuntarily stopped in a portable way. So there's a couple of different ways to stop them voluntarily. Using a Boolean flag that's volatile is one approach. But we talked about why that had some deficiencies. In particular, if you're in a blocking call, then using this flag doesn't really help you. So the other way to do it is by calling the interrupt method, which is used to disturb a thread. And we'll talk about what happens when that occurs. So when you call the interrupt method, that posts an interrupt request to a thread. And this is something that's done internally to the thread implementation. It's got some magic built into the internals so it works in a more consistent and powerful way. Internally, interrupts are implemented via an interrupt status flag. And when you say interrupt, it sets that flag, and then various parts of the implementations, either in the internals of Java or in code you write, get to check that status flag by making various calls. So you call interrupt, that sets the flag, and then the program can check this flag by two different accessor methods. One called interrupted, and we've talked about this before. This tests whether the current thread has been interrupted. And this is a static method, as you can see up here. And one of the consequences of calling interrupted is it also resets the flag, so it is no longer interrupted anymore. And the other method is interrupted, and this is not static. You have to call it on a particular thread instance. And it also checks whether the thread has been interrupted. But unlike interrupted, it does not clear the flag. So each of these methods have different side effects on the interrupt status. And we'll talk about some examples, and you'll see how it all works. So here's a very simple program we're going to use to kind of demonstrate these ideas. In this case, we have a main program. And we go ahead and make ourselves a new thread. And then we start the thread. And inside the thread, we're going to loop for some period of time over the arguments or whatever. And we're going to call a couple of different methods. One method is going to make blocking calls where interrupts are handled by the internals of Java. And the other is going to be calling non-blocking calls where you explicitly have to check to see whether or not the thread has been interrupted. So there are two different ways to do this. Let's assume that after we start the thread, we do some other stuff for a while, ... things run concurrently. And then at some point, the thread is going to be interrupted. So what we'll do here is we'll see how this implementation takes place. So here's the process blocking implementation. And as you can see in this implementation, we're going to go ahead and make calls to sleep and wait. And these are blocking calls. And what that means is that we don't really know how long they're going to run. They may block for a while. They may block for a short time. In the case of sleep, it'll block for however long you told it to sleep, and so on and so forth. And when those calls are finished, they'll return. But if the thread is interrupted while those things are blocked, then the interrupted exception is automatically propagated by these calls, and then you're given an opportunity to catch it and do something with it in one way or another. And we'll see that there's a lot of different ways you can handle it. So it turns out that things like wait, join, sleep, and then various blocking I/O calls on so-called interruptible channels, these are all things that the internals of Java, the Java library implementations, will automatically interrupt for you and throw an exception so that you know that something has gone wrong. Conversely, here's another set of code. This is going to be processing methods that aren't blocking. So you have to make the calls yourself in your code to see whether or not your thread is interrupted. And here's a way to do this. You'll have a loop, and while the loop is, you run forever, if the thread has been interrupted, and this is the interrupted method, this is the static method call that's going to set that flag, then you'll have to make the check. And notice that this will go ahead and reset that flag. In this particular case, what we're going to do is we're also going to throw a new interrupted exception. So we're going to notice that it was interrupted, and we're going to throw the interrupted exception, and then it's up to the caller to figure out what the heck to do about that, because that's just typical exception handling in Java. So this method's going to throw an interrupted exception, and again, notice, as we say here, that it's going to clear the state of this flag. And that's important, and we'll see how you have to have various patterns for propagating the exceptions properly in some circumstances. A Java exception is allocated and treated just like a normal object. So it's treated like an object in the sense you create it with a constructor and so on, but notice it goes up the call chain of the stack until it's either caught and handled or until it falls off the end of run or main, in which case you'll get an uncaught exception error unless you've set an uncaught exception handler. And there are various ways of doing that as well. So in contrast, here's the use of isInterrupted. This does not reset the flag. And notice how we have to get an explicit thread ID in order to do this check, because it works off of a thread ID, not the default thread, the way that the interrupted method did. And therefore, you can call it multiple times without affecting its interrupted status. As a little piece of trivia, you can actually override the interrupt and isInterrupted methods. It's possible to override those things if you so choose. And there's reasons for doing that, but it's a rare thing to do. So if you ever find yourself compelled to override these methods, take a look on the web, and you can take a look at this link, which I will fix in the PDF version of the slides, and learn why you might want to do this and what some of the consequences are. The key thing to remember is if you decide to override the interrupt methods, you need to call up to the superclass version for things to work properly. So what I'd like to do now is talk about the differences between thread interrupts and hardware and operating system interrupts. So if you've ever taken a computer system organization course or an operating systems course, hopefully you've learned something about hardware or operating system interrupts. It's a very low-level way of doing things. And you can learn about that by taking a look at this link. You can also learn about something that's called signals, which is a form of a software interrupt that the operating system layer handles. And here's a picture that shows different ways things work. So you have hardware, processor, and software interrupts. So here are the characteristics of these types of interrupts. So an operating system or hardware interrupt is typically asynchronous. What does that mean? It means that it can occur essentially at any time, and it's independent of the instruction or instructions that are currently running. So these things can kind of come out of left field, and they're usually an indication of something, either an error that's happened or, in the case of the operating system, some hardware device that has gotten something and wants to get the attention of the CPU. For example, a network interface might use interrupts to be able to inform the operating system that a new packet has shown up. So it's a way of getting its attention. So the other thing to remember about these kinds of interrupts is the program doesn't need to explicitly test for them. They're generated automatically, so you don't have to sit there and check. You'll know because the interrupt handler will get called back. And the way that typically works in practice is when an interrupt occurs, the underlying operating system will make a new activation record to indicate the exception handler, which is a function, and it'll just stick it on top of the runtime stack. So it blocks whatever else is going on at the moment. That is where the control is transferred to. You do something, and then when the interrupt handler is finished, that pops off, and it continues where it left off earlier. Another consequence of hardware or operating system interrupts is that they are preemptive. And what that means, as I just described with the way that the runtime stack works, is that the current thread of control is automatically paused, and the exception handler or the interrupt handler is run. And then when the interrupt handler is finished, then control resumes where it left off. And that's, again, just using the typical runtime stack behavior. But the point here is that the the current activity, the current thread, the current behavior is pinned while the interrupt handler is run. And so it's preemptive. It preempts whatever else happens to be taking place at that point. Here's a very simple example, which you can, if you're a Unix programmer, you could compile and run to see how it works. This shows how to catch the Unix sigint signal. And the sigint signal is typically generated by typing Control-C in a Unix shell. So if you have a Unix program and you run it, and then you decide, oh, I don't really want to run this thing, you can type Control-C, and that sends the sigint signal from the command shell to the running process, and it handles it in some way. So this illustrates how to do this. So you go ahead and have a main program. You set up a signal handler, sig handler, and that's just a callback. Sig handler is a callback function. And then in this particular case, we go and we just sleep for 10 seconds. And while we're sleeping, we would type Control-C, and that would then cause this excuse me, signal handler to get called back, and that would then check to see what signal occurred, and it would print out SIGINT if that was the signal that occurred. So notice this occurs asynchronously. It preempts the current instruction, which is asleep, and we don't test for it explicitly. A handler just gets called back, and we deal with it. So that's a software interrupt that's done by the operating system. And there are hardware interrupts that are done in the operating system kernel that work very similarly. The key thing to remember is a couple things. First of all, this turns out to be tricky. So let's talk about why is it tricky. Asynchronous and preemptive interrupt handling makes it difficult to reason about programs. And you can read this link to find out more about why that is, and I'll give you some examples of why. One reason why it's tricky is that there can be race conditions, where it may turn out that you are in the middle of doing something and you get interrupted, and this will go ahead and overwrite some value that was being used in a different context, and then an interrupt handler occurs and it goes ahead and it makes a change. So you have race conditions. That's one potential problem. Another problem, which is related but not identical, is this concept of reentrancy. So reentrancy says if something is reentrant, you can call it again and it will work properly if it's called again while an earlier version is already running. Conversely, a non-reentrant function cannot be interrupted in the middle of its execution and then safely called again before its previous invocation or invocations complete their execution. So what the heck does that mean? Well, I'll give you an example. This is a classic problem that you run into with reentrancy. If you were in a program, let's say a Unix program where signals can come in asynchronously and preemptively, and you had just called malloc or new, depending whether you're in C or C++, then at that point when you call malloc, the underlying library, the underlying C library or C++ library, will start to rearrange the heap or the free store. So it's going to try to allocate you a chunk of memory that's big enough for whatever you're trying to do. And while that's taking place, the data structures that are used to implement the heap or the free store might be in an inconsistent state, right? It might allocate some memory and it might be about to stick it into a linked list or update a linked list. But at some point, the data structures might not be completely consistent, which is normally okay because you're not expecting anybody to interrupt you while you're in the middle of something. But if a signal was to occur while the data structure was in some inconsistent state, and then in your signal handler you were to call new or malloc again, then what would have happened was you would have left it in some inconsistent state when you were interrupted, and now you're calling back into the free store or the heap, and it's in some crazy internal state, and so the second call will go ahead and break because the previous call didn't get to finish whatever it was doing. So that's an example of a non-reentrant program behavior. There's lots and lots more. And for that reason, it's often the case that you want your signal handlers to do very little. In fact, the typical thing you want them to do is like set a flag, and that's about it. But anyway, that's one of the problems with reentrancy. And then there's a third problem, which are called non-transparent restarts. So it turns out that you might be blocked in a long-running operation like a read or a write. And that is going to return the number of bytes that it read or wrote to while it's blocked. Well, if you end up having something that is interrupted, then it may not restart things in quite the right way. And so you need to make sure you keep track of what's been happening. So again, take a look. You can read more about that. If that seems a little confusing, you can read about restarts on calls. The bottom line is that asynchronous and preemptive interrupt handling is tedious and error-prone to deal with. So with that in mind, the key thing to remember is that Java thread interrupts don't behave the same way that hardware or operating system interrupts do. And there's reasons for that, and the reasons are to try to make it less complicated to avoid all these problems we just talked about with race conditions, non-reentrancy, and non-transparent restarts. So Java thread interrupts use synchronous and non-preemptive semantics rather than asynchronous and preemptive semantics. So what that means is they don't occur at an arbitrary point in time. They only occur at very well-defined points in time. And typically, you either have to check for them, or you've called a blocking call that's interruptible, and it checks for it on your behalf. So what it does is it doesn't occur at arbitrary points in time, and it doesn't pause and later resume running code. You, the programmer, or you, the library developer, have complete and total control over when the interrupts are going to be checked for. In particular, a program actually has to test for them explicitly. So just like we've been looking at up to this point, if the thread is interrupted, then we check for the thread being interrupted. The thread doesn't get interrupted in an asynchronous or preemptive way. The flag is set, and then we have to synchronously and deliberately do the check. So typically, interrupted exceptions are thrown synchronously and handled synchronously. So it's less confusing. Now again, for those people who've come from an operating system or hardware background, they don't quite get this, and they don't understand Java semantics. And that's why I explained the hardware stuff first, so you could see how it works internally at a lower level, and then why they chose not to do that. Now it turns out, and this is really, really, really annoying, in fact, annoying enough that it's actually considered a bug, that certain operations in Java cannot be interrupted. In particular, blocking I/O calls that are made on things that are not interruptible channels. And here's a very simple example, and it's extremely frustrating. Here's an example that's going to read in basically a character at a time or an int at a time inside of some thread, right? We're just going to sit here reading in this thread, reading in a character at a time. And this call, this read call, as you'll discover when you read this bug report, this cannot be interrupted. So there's no way to interrupt that thread while it's blocked in the read. And I think that's completely wacky, because it means that in many situations it's very hard to stop something from reading. And so you actually have to do some other tricks. You have to set your stuff in non-blocking mode and so on, or use interruptible channels and so on. So it turns out to be a bit non-intuitive, but be aware that there's some things in Java that are very hard to interrupt. Okay, let's now talk about patterns of stopping Java threads via interrupts. I've told you a bit about how they're synchronous and non-preemptive. Now let's talk about what you have to do in order to program them effectively. So like almost everything else in computing, people who are experts at something have a set of rules and patterns that they follow to help make their code more robust and bulletproof. And if you take a look at this link at the bottom of the slide, you'll get to read about what I'm describing in more detail. Anne?
So the blocking methods, they check the interrupted status and throw the exception if it's true?
Certain blocking methods do. So wait, sleep, join are blocking methods that will check internally to see if it's been interrupted. If you do I/O operations on so-called interruptible channels, then they check. But sadly, certain things in Java, like those reads that we just looked at, which are non-interruptible channel reads, those don't actually do the check. So you're just stuck there until something happens. So you have to use other techniques in order to deal with that. Okay, so let's talk about, this is the article that you can take a look at. So the main issue here is, if an interrupted exception occurs, what do you do with it in your code? How do you handle it? And it turns out there's several different ways to handle it. One way to handle it is to propagate the interrupted exception to callers by not catching it. In other words, take a look here. Here's an example where we've got some kind of queue, and we've got a put and a take method. And put and take are going to call down to queue, put and take. And this is going to be a blocking queue. So this will block. If you try to put and the queue is full, it'll block. If you try to take and the queue is empty, it'll block. And what happens here is if the thread is interrupted, we're not going to handle it in our put and take methods. We're simply going to let the exception that's raised here, the interrupted exception, propagate up to our caller. So that means it's somebody else's problem to handle it. It's not our problem. We're just going to propagate it up. They can deal with it.
Okay,
Yes?
so when in the skeleton code, when it says, so when you have a method that says it explicitly throws it, it's basically saying I'm not dealing with that. It just throws it back up. And if you don't have a throw and you use a try catch, you have to deal with those.
If it's, yeah, so the question is, what is this? This is something that's caused, this is called a throw clause. And remember in Java, there are two different types of exceptions. There's checked exceptions and there's runtime or unchecked exceptions. The only difference is a checked exception is actually checked by the compiler, whereas an unchecked exception is not. So when you have code that looks like this, if we didn't have throws interrupted exception, then we would have to have a try catch block here because this method throws the interrupted exception. And so we'd have to deal with it. So one way to do it is to deal with it. The other way to do it, which is what we're showing here, is not to deal with it and make it the caller's responsibility to deal with it, or not, right? They can do the same thing. So, I mean, eventually it'll propagate up to the outermost levels of your run or main methods in your thread or program, and then somebody will have to deal with it. But we're not dealing with it here. We're basically passing the buck, as it were. We're making it somebody else's problem.
So it allows you to consolidate all the exception handling to
Right. So the observation, which is a good one by Philip, is that the exception handling is being pushed up the stack, and someone will have to deal with it, but we'll put it maybe at the outermost level, which is one way to do things. Not always the best way to do things, but it's one way to do things. Yeah, Anne?
So if like put is called by another method, would that method also have to say throws interrupted exception into passive?
Right. So the question is, if we have a program that's going to call put and take on an instance of string blocking queue, then what does it have to do? Well, it could either do this trick and propagate it up by not handling it, or it could put a try catch block. So it's got a couple of choices. It depends on whether you want to centralize your handling or whether you want to deal with it. Sometimes you want to deal with it where you are. All right, so that's one thing. Deal with the problem by not dealing with it. You just say, okay, it's deliberately somebody else's problem. Another thing to do is to perform some kind of task-specific cleanup and then rethrow the exception. So you can see here's a snippet of code, and we're doing a check, we're waiting. If the interrupt occurs while we're waiting, then what we do is we're ultimately going to rethrow this exception. Notice how we take exception E and we're going to throw it down here. But before we throw it, we're going to first do a little check to see whether we have to clean some things up. And I won't go into the detail of what the code is doing under the hood, but in a nutshell, it's basically trying to remove a lock, and if it was unable to do that, it's going to go ahead and release something. So the point here is we're trying to avoid leaking resources or leaving the resources in an inconsistent state. So we're still going to make it somebody else's problem. We're still going to propagate this exception by throwing it up the stack, but we're going to clean things up first for whatever reason we need to clean things up. Yet another thing to do, and by the way, these are not entirely mutually exclusive. They're just different ways of handling these problems or these issues with exceptions. Another thing we can do is we can restore the interrupted status after catching the interrupted exception. So you can see here that we've gone ahead and done some stuff. We're here waiting for up to 10 seconds to get an item from the queue. And if an exception occurs, then we're going to do some cleanup or whatever. And then we're going to go ahead and reset the interrupted status flag to indicate an interrupt has happened. Because when we catch the exception, the flag is cleared. So if we want the caller to see the exception, we need to reset it. And if you take a look at your assignment, that's what we do, right? We have to reset it. So that means that somebody else up the stack will have to deal with it. And then another thing that people often do, although this usually gets you into trouble, is they go ahead and handle the interrupt and swallow it. So in this particular case, we're going to wait for a certain amount of time, and then if an exception occurs, we're going to return false, but we're just going to swallow the interrupted exception. We're not going to propagate it. We're not going to do much. We're just going to say, yep, something happened. It returns false. Be very careful. It's tempting to swallow interrupts because they seem a little annoying at times, and you're never quite sure what to do with them. But swallowing the interrupt is almost always the wrong thing to do unless you're just writing a piece of test code or throwaway code. It's usually better to do one of these other things. Propagate it to callers by not catching it and putting it in the checked throw clause, perform some task-specific cleanup, and then rethrow it, restore the interrupt status after catching it, et cetera, et cetera, et cetera. So there's a bunch of other things to do, and this is often not the right thing to do. All right, so just to kind of summarize interrupts, it turns out that if you want to stop Java threads, you've got to cooperate, like so many other things in life. You can't just come along and by fiat or by dictatorial decree say, you must stop. You actually have to negotiate. Threads, therefore, need to check periodically to see if they've been told to stop. We've talked that there's a couple different ways to do that. One of the consequences of this, however, is that thread interrupts are very fragile because it requires all parts of the program to follow these consistent usage patterns. And if somebody decides they're not going to play along, or they get sloppy, or they don't really understand the rules in the first place, then it's very difficult to write code that will work properly with interrupts. And this article here talks a bit about the challenges of dealing with interrupts. So it would be nice if there was some other way to do it, but in Java, voluntary checking is the way to go, right? It's tedious, it's error-prone, you get yourself into trouble, but it's really the only way to stop Java threads in a reliable way. So it's good to get in the habit of doing it. And that's, of course, why your assignments give you a chance to learn how to do that. OK, so that's the end of that lesson.